You might think to multiply two matrices, all you need to do is to multiply the corresponding entries. But that turns out to be not the most useful thing in business. What turns out to be useful is when you multiply a row of a matrix by a column of another matrix. Then the corresponding entries are multiplied and then added up. So let's take a look at an example. So here I have a row matrix that consists of the row 1, 2, 3, and I have a column matrix that that has the entries 4, 5, and 6. So what I'm going to need to do the matrix multiplication between those is I need to start corresponding my entries. So you'll notice that I've put it in color here. I have in red the 1 and 4, in blue the 2 and 5, and in magenta the 3 and 6. So I correspond those entries and multiply, and then I add it to corresponding entries multiplied, so now the blue ones, and now I add that to corresponding entries multiplied. So I end up with 1 times 4 plus 2 times 5 plus 3 times 6, which gives me 32. Notice that the result is actually a matrix, and in this case it turns out to be a 1 by 1 matrix. In other words, it has one row and one column. So the definition for matrix multiplication is this. Let A be an m by n matrix, and let B be an n by k matrix. Notice that the number of columns in one matrix matches up with the rows of the other one. To find the entry in the ith row and jth column of the product AB, we multiply each entry in the ith row by the corresponding entry in the jth column, and then add these products up. The result is an m by k matrix. So you can see in this definition that we're multiplying corresponding entries, and then we add everything up. So for instance, it said we have an m by n, and we're going to multiply it by an n by k. In order to be able to match things up, the columns in the first matrix have to match with the rows in the other one. Then the result is just the other two entries. In other words, the result is going to have a size where the rows come from the first matrix, the m, and the columns come from the second matrix, k. So let's do an example. What you see here is I have a 2 by 3 matrix with the entries 1, -1, and 0 in the first row, 2, 3, and -3 in the second row, and I'm multiplying that by a 3 by 1 matrix that has one column with 1, 2, and 4. So here I've written down the sizes, and we first need to make sure that you can actually do this multiplication. So I look at these insides and I see that the columns of one matches with the rows of the other. So that tells me I can actually carry out this multiplication. Now I need to figure out what the result is, and that comes from the outside entries here. So this is going to be a 2 by 1 matrix, so I'll go ahead and put it in here. In the first row, first column, I go to the first row of the first matrix and the first column of the second matrix, and I match them up. So you see this in red now, so I take 1 times 1, -1 times 2, and 0 times 4. So when I work out those products and add them all up, I get 1 minus 2 plus 0, that's -1. And that's what goes in the first row, first column. In the second row, first column, I go to the second row, first column, and now that's in blue, and I make up my corresponding products. So 2 times 1, 3 times 2, and -3 times 4. I work out the products, 2 plus 6 plus -12, and that gives me -4. Now let's take a look at another example. In this case now, we have 3 rows, 1 column, and 2 rows, 3 columns. These are the same matrices I've had before, But now I've reversed the order in which I'm doing the multiplication. So I'm taking a 3 by 1 times a 2 by 3, and when we look at that, the columns in the first matrix do not match up with the rows in the second, so there's no way I could match a row with a column here and get corresponding entries. So when this happens, we say that the matrix multiplication is not possible, or we say it does not exist. Either one of those answers is perfectly adequate.